We need the Fourier transform because it helps us understand and analyze signals such as music or images in a more meaningful way. Imagine you're a scientist studying a mysterious sound from outer space. You record this sound using a special microphone. Now, this sound is quite complex, with many different frequencies mixed together. By using the Fourier transform, you can break down this complex sound into its basic frequency components. This helps you identify if there are any specific patterns or frequencies that stand out. It's like taking a jumble of sounds and organizing them neatly, so you can see if there's a particular note or rhythm that repeats. Similarly, in image processing, the Fourier transform can help us break down an image into its basic spatial frequencies. This can reveal patterns or structures that might not be obvious at first glance. For example, it can help us enhance certain features in medical images or remove noise from photographs. So, in essence, we need the Fourier transform because it's a powerful tool that allows us to understand and manipulate signals in various fields, such as physics, engineering, mathematics, and more. It helps us extract meaningful information from complex data, enabling us to make better informed decisions and discoveries. Just like how we can use the Fourier transform to break down complex signals like music or images, our ears naturally perform a similar process when we listen to sounds. When you hear music or any sound, your ear acts like a natural Fourier analyzer. It receives the sound waves, which are essentially combinations of different frequencies, and your inner ear's cochlea helps to break these complex sound waves down into their basic frequency components. This breakdown of frequencies is essential for us to perceive and understand sounds. It helps us distinguish between different sounds, like a bird chirping versus a car honking. Just as the Fourier transform helps us analyze signals in science and technology, our ears use a similar process to help us make sense of the sounds around us. Sound, at its most basic, is a wave that travels through the air or other media. These waves are created by vibrating objects and propagate through mediums at various speeds depending on their density. The human ear detects these vibrations and translates them into signals our brains recognize as sound. Frequency, a key concept in understanding sound, refers to the number of wave cycles that occur in a second. Low frequencies produce deep sounds, while high frequencies create high-pitched sounds. Fourier transform helps in identifying these frequencies, making it easier to analyze and manipulate sound. Fourier transform originates from the work of Jean-Baptiste Joseph Fourier, a French mathematician. By suggesting that any function can be split into a series of sines and cosines, Fourier revolutionized how we interpret data signals. This principle is especially useful in sound analysis, where complex audio signals are broken down into their simplest forms for easier interpretation and manipulation. The mathematical elegance of Fourier transform lies in its ability to convert time domain data, sound signals over time, into frequency domain data. This conversion is crucial for various applications, from telecommunications to medical imaging. Fourier transform has applications that reach far beyond theoretical mathematics and sound engineering. It is integral in the functionality of many devices and technologies that impact our daily lives, from MRI machines that image our insides to the JPEG images that populate our digital worlds. In the realm of telecommunications, Fourier transform helps in the compression and decompression of audio and video signals, ensuring they are efficiently transmitted and stored. The human ear is divided into three parts: the outer ear, the middle ear, and the inner ear. Sound waves travel through the outer ear and hit the eardrum, causing vibrations. These vibrations are amplified by the ossicles in the middle ear and transmitted to the cochlea in the inner ear, where they are transformed into electrical impulses. Fourier transform comes into play in the cochlea, which acts almost like a natural Fourier analyzer, breaking down sounds into their frequency components. This decomposition helps the brain to perceive and distinguish between different sounds. In the development of hearing aids, Fourier Transform plays a pivotal role. By analyzing the frequencies that a person struggles to hear, engineers can design hearing aids that amplify these specific frequencies, thus improving the clarity and quality of sound for the user. This tailored approach not only enhances the effectiveness of hearing aids, but also contributes to a better quality of life for the hearing impaired. Fourier Transform is indispensable in the field of music, from the analysis and synthesis of musical sounds to the development of electronic music instruments and sound editing software. By breaking down complex musical compositions into identifiable frequencies, musicians and technicians can alter or enhance specific aspects of the sound, creating richer and more varied auditory experiences. The impact of Fourier Transform on speech recognition technology is profound. By decomposing speech into its frequency components, this mathematical tool helps in the accurate identification and interpretation of words and phrases. This capability is critical in developing more effective voice-activated assistants, enhancing accessibility features, and improving communication devices for the speech impaired. Fourier Transform is a key player in neuroacoustic research, which explores how our brains process sounds. By understanding the frequency patterns that our brains prefer or avoid, researchers can develop better auditory therapies and technologies, potentially aiding those with various types of auditory processing disorders. The study of animal hearing through Fourier Transform provides insights into the evolutionary aspects of auditory perception. By comparing how different species process sound frequencies, researchers can trace the development of hearing capabilities across the animal kingdom, offering clues about our own auditory evolution. The future of auditory research with Fourier Transform holds exciting possibilities. From developing superhuman hearing devices to enhancing sound resolution far beyond current capabilities, the potential applications are boundless. As with any technological advancement, the application of Fourier Transform in auditory enhancement and manipulation comes with ethical considerations. Issues such as privacy, consent, and the potential for misuse must be carefully managed to ensure that these innovations benefit society without infringing on individual rights or freedoms. As we conclude our exploration, it's clear that the Fourier Transform is more than just a mathematical tool. It's a fundamental component in the symphony of science that is sound. From enhancing musical experiences to revolutionizing hearing aids, its applications are as diverse as they are impactful. As we continue to study and develop this tool, the future of sound perception and manipulation looks both promising and infinitely intriguing. Music to math. The Fourier Transform is a mathematical tool that has profound applications in music, allowing us to analyze and understand the complex mix of frequencies in musical compositions. Image magic. In image processing, the Fourier Transform helps us break down images into their basic spatial frequencies, revealing hidden patterns and structures that might not be visible to the naked eye. Nature's analyzer. Just as the Fourier Transform helps us analyze signals in science and technology, our ears naturally perform a similar process, breaking down complex sounds into their basic frequency components so we can understand and perceive them. Space sounds. Scientists use the Fourier Transform to analyze signals from outer space, helping them uncover the secrets of cosmic phenomena like pulsars, black holes, and gravitational waves hidden within the vast universe. Medical marvel. In medical imaging, the Fourier Transform aids in enhancing features in images such as MRI scans, allowing doctors to diagnose diseases more accurately and provide better patient care. Communication revolution. The Fourier Transform is at the heart of modern communication technologies like Wi-Fi, cell phones, and digital broadcasting, enabling the transmission and reception of information across vast distances with remarkable efficiency. Security Sentry. It plays a crucial role in encryption algorithms, ensuring the security and privacy of sensitive information transmitted over the internet, safeguarding our digital communications and transactions.